Hello YouTube, welcome to this video. Today I will be talking about the Euler development of cotangent, which is this thing, and I will demonstrate entirely with the hard proof because there is an easy one, but I'm going to do the hard one. So it's kind of complicated. The sum starts at minus infinity to plus infinity, so it's kind of hard, and it's also very long because this demonstration is in 10 parts. So yeah, so let's start. So I'm going to start with the first properties of cotangent. I call f of x the function cotangent of pi x, which is 1 over tangent pi x. So the thing, why do we put the pi here, is that because cotangent cancels out, well, is not defined when pi, for integers, but for pi times integers, but factorizing by pi makes so that the the function will not be defined for integers and not pi times integers. So the function f is correctly defined, continuous and c infinite in the space of reals minus all of the integers. So if we have put like this, we needed to have pi here. So yeah, okay. So the first thing we're going to do is calculate f minus x. So we replace with the expression of tangent with sine above and cosine down, but since it's the inverse, we get this, and then we get that f of minus x equals minus fx. So we can say that f is odd on its interval of definition. So we're going to what's going on? Hello? Okay. So we're going to calculate f x plus 1 because we're going to try to prove the periodicity. So we get this, and the fact that there is plus pi on the cosine part will put a minus sign, and since it's the same in the sine function, you'll get fx plus 1 equals f of x. So every time you add 1, function is 1 periodic, so every time you add 1 you'll find the same result. But it's true for all numbers that are not integers. So 0 is not defined, 1 is not defined, but 1/2 is defined, and f of 1/2 equals f of 3/2. Okay, so let's move on to part 2. The property p for f. So I call p the following property. The function key verifies for all x inside the reals minus the integers. Chi of key of x over 2 plus key of x plus 1 over 2 equals 2 key x. So yeah, so let's do that. So in that interval we calculate this and we develop, so we get this expression just by replacing with the expression we got earlier, this one. With this expression we know that if we have plus pi over 2, it equals to minus sign for the cosine. For the sine, the plus pi over 2 transforms into a cosine, so we get this expression. And then we can factorize like this, and then we can get into this step by using formulas for sine times cos, that will get twice what's inside this, and one for what's below we'll get twice what's here, composed by sine, and 1/2 here. So here it's multiplied by 2, it's here. We have the sine that is here, and we have 1/2, but the 2 goes here. And for this part, cos squared minus sine squared, it equals to cos 2 what's in here. So we get the cos and 2 what's in here, so this. And we have the pi that is factorized, obviously. Okay, so we get actually twice f of x, which is like this is just twice f of x, like here. So f v5 is p, which is cool. Okay, so 3, I'm going to talk about the properties of g of n. So what's g of n? I call g of n and g. G of n is 2x. I'm going to zoom in. Maybe I can just make it bigger. Small. So g of n is 2x over x squared minus n squared for n superior or equal to 1. And g0 is equal to 1 over x. So technically this could be defined for 0 with this, but it does not give the result that we want, so we're not using it. And g of x is just the sum of the gn from 0 to plus infinity. So gx is defined because this series actually converges simply because it's equivalent to a series minus 2x over n squared in plus infinity. And since this series exists, since this series converges, then this one converges too. Oh yeah, and also after a certain rank that exists, Gn is strictly negative. And obviously it depends of x, but we're not precising which one. We could do that, but it doesn't really matter. We just know that after some rank, since there is this, and this doesn't change sign, so we know that this converges, so this series converges simply too. Now let's do the let's calculate g of n of minus x. We just expand and we get that it's equal to minus jn of x. So gn is odd, and by summing, g is odd too. Okay, so let's talk about the continuity of g. Okay, so we start with the hypothesis of n is superior to 2. So Gn is derivable between 0 and 1 because there is no problem, like nothing special, because the problems that will appear will be in 0 and 1, so we don't have any problem here. And we get this derivative. It's just the formula. It's just the formula to calculate the derivative. And it's strictly negative because this is positive, and because this is strictly positive because it's a squared, and this is the sum of two squared, so it's positive, and we're in reals. And there is the minus sign in front, so it's negative or 0. So it meant that this is negative or 0. So g is always decreasing. But g of n in 0 equals 0. So we know that g n of x is always negative. So yeah, for n superior to 2 and for x between 0 and 1 excluded, the absolute value of gn of x is inferior to 2 over n squared minus 1. So this comes from, wait, where is it? Here, because after n equals 2, you can just get this approximation. Well, it's not an approximation, this inequality. Okay, But we know that this is the general term of a convergence series, so if you sum that, it converges, because it's the form 1 over n squared. So it means that this converges, so the sum of the series of Gn converges, but the sum of absolute value of Gn converges too. So it means that this converges normally, starting from 2, because we started from 2 here. And so the fact that we started from 2 allows us to get this expression. And we know that we already know G0 and G1. So the expression of G1 is just replacing from here with n equal 1, n equal 1. So this converges normally, so it's continuous. And this is continuous on the interval as well. So if you sum this and this, so all of this, you'll get G, and G is continuous. Okay, so now I call Q to be equals to the floor of absolute value of x plus 1 of squared. So for all n superior to Q, we get that T, okay, so I didn't explain what's T. So wait, I'm going to copy this. Okay, so for all T between floor x and floor x plus 1, T is inferior to floor x plus 1 because of this. And also we get this inequality, it's from the definition. And this is inferior to square root of n due to this thingy here, because the rank says that it's superior to Q. So we get this inequality, and we can get this thingy here by replacing with T. So we get this inequality, so Gn applies in T is inferior to 2 square root of n over n squared minus n. So we get it from the formula applied in square root of n. So we get this inequality. And I just take the important terms, and I get that it's inferior to 2 over n to the power 3/3, and that's it. Yeah, and this obviously is the general term of a convergence series. So this converges too. Okay, so we have oops, I've written this twice. Okay, so we know that this converges normally for all values of x in floor x plus 1 for all values of x. So obviously this x is not the same x as here. So for all, how can I say it? Oh no, it works fine. It's fine. And all the functions are continuous. And all of these functions are continuous because we've proved it earlier. And obviously this sum is starting from Q because of the hypothesis that n is superior to Q. But we also know that the functions G0, G1, G2 until G, Q minus 1 are continuous. So the sum of this plus this that we've already proven that it's continuous is continuous as well. So G is continuous in the space of reals minus without the integers. Okay, so now the fifth part, the one periodicity of G. So we study G of n applied in x plus 1. So we get this from its definition. And we can expand this with the formula. When you have a squared minus b squared, you get this. And it's kind of tricky to get that this equals to this, but like you can see it. You can see that there is something related to that. And if you make that in a single fraction, you'll figure out that it's the same. Okay, so I call big G of n of x to be equal to the partial sum. So starting from 0 to big N of the small g n of x for n superior or equal to 1. So if it was equal to 0, it wouldn't be defined. Or I guess it would be g0. Yeah, it would be g0. Okay, but it's still superior to 1 because of things we'll do later. So gn, yeah, because g0 is not defined correctly, but whatever. Well, it's defined correctly, but it's not the same definition as gn for n superior to 1. So gn of x plus 1 equals to this. So this comes just from the definition and splitting. Yeah, yes, just from splitting. Okay. What else? What else? Because so basically, it's the definition, but we have spliced the term in n equals 0. So instead of starting from 0, start from 1, and the term in 0 is here. So we get this expression, and we realize that this. What am I saying? We realize that this expression, we can see that we have the expression of gn of x, but without some terms. So the first ones. And by the change of indice of the n, we can get this. It's not that hard. It's just like changing the value inside the sum. Okay, so we take the limit. So the limit of this part here, this one, is g x plus 1 from the definition. This is just literally the definition of a series, series. So yeah, and this part here converges to g of x, and both of these converges to 0. So by continuity and by taking the limits of gn of the expression we got here, we get that jx plus 1 equals jx. So G is one periodic. Okay, so now we are going to prove that G verifies P. Okay, so we do the same thing as before for F, but now with a big G of n. So we expand, then we that's just expanding. Yeah, that's just expanding. And we get 2g of n from this part. Wait, where is it? This part here? No, this part here. I'm confused. Oh no, it's because we put in a single fraction, because we factorize that and we factorize that. So we get 2g of nx and twice this. So we sum this between. Oh wait, what am I saying? This is actually not the same expression as this, because this is big G of n, this is small g of n. Because well, this is the partial sum, and this is not the sum, this is just the regular g, small g. Yeah, yes, okay. Whatever. Yes, so we are going to sum this expression between 0 and big N. So we get that we get this by just summing. This is just summing. When you sum this, you get this, and when you sum that by summing, you get this. So yeah, okay. And then you take the limit when yes, okay, it's fine. Yeah, it's fine because of the terms in 0. Okay, whatever, forget it. It's fine. Yeah, it's correct. So take the limit when a big N goes to plus infinity. So this goes this goes this goes to 2g, and this goes to 0. So g verifies p. So now the convergence of f in 0. F, yeah. So the f converges to 0, but we'll try to see if it converges to 1 over x. So at first I called h the expression f of x minus gx. So it equals to pi cotangent of pi x minus 1 over x minus the sum from 1 to plus infinity of what we said earlier. H is continuous, defined, odd, and one periodic and verifies P because we sum F that is continuous, defined, odd, one periodic and verifies P, and G that is continuous, defined, odd, one periodic and verifies P. Okay, so I calculate f of x. I get this expression. I do a limited development, so I get this expression here. And I do the same limited development here, so I get this expression. But I studied this part here that is just what's on the bottom. So this equals to this by factorizing by 1 over x. And the pi gets away because of the fact that it's the O operator, so it doesn't really matter. So we get this, yeah. What else? So I continue. So I do a limited development of 1 over 1 plus x in 0, obviously. And I get this expression here. And actually all of this equals O of x when x goes to 0. So we get this expression. Okay, pretty fine so far. So I get there is a missing sign here. Yeah. So I get this expression of f by just replacing, and that equals to 1 over x plus O of 1. So we can know that the limit of x to 0 of f minus 1 over x equals 0. Okay, so we just proved the equivalent in 0. Okay, now 8th part, the continuity of h. So at first we do the hypothesis that x is superior to is inferior to 1/2. So I take the absolute value of this and I just simplify, so we get this expression. I just factorize by 2, that doesn't really matter, and x that isn't summed, so we can just factorize. So I get this expression. So this expression is inferior to 2. It just comes from this correlation. It's not really hard. And we also get this expression for n superior to 2. So it's just saying this expression. So we can do this. We can do this inequality, get this inequality. So we get 2 absolute value of x times something, but we can say that this is a constant. Well, actually twice this is a constant k. So we know that we've got k disk that is a constant. So we know that this the limit of this when x will go to 0 is 0 because we've got x times a constant, because this doesn't depend of x. So we've got this that's actually h. What am I saying? Oh yeah, the limit of 0 when the limit when h goes to 0 is 0. Yeah, yeah, yeah. It's this. The limit of hx when x goes to 0 is 0. So h is continuous, one periodic in the space of reals without the space of reals of integers. So for all integers, the limit limit of oops, what the fuck? What am I saying? Yeah, it's this. The limit when x goes to 0 with x different of 0 of h of x is the same as is the same for any integers actually, and that equals to 0 because it's h of k. Okay, so h is continuous on all integers as well. So we know that h equals to 0 for all integers. Okay, so now I'm going to calculate the value of h. So h is continuous on the compact 0, 1 as a sum of a continuous function, because this is continuous, this is continuous, this is continuous. And on the compact 0, 1, so 0, 1 is a compact, and when you apply a continuous function on a compact, it's a compact. So you can define m as being the maximum of h of x in the compact 0, 1. So there exists x0 in the compact 0, 1, so that m equals h of x0. So we apply the property p in x equal x0. So we get this, and we get that it's equal to 2m's. But x0 is inside 0, 1, so x over 2 is inside 0, 0, 1, and 1 over 2, 1 half. So x0 over 2 is between 0 and 1. And the same reasoning for x0 plus 1, it's between 0 and 1 as well. So we get that this will be equal to 2m's, but we know oops, there is a minus sign here. So we know that h of x0 plus 1 over 2 is inferior to m, and h of x over x0 over 2 is inferior to m. So we get that hx0 over 2 is superior over 2m's minus m from this line, so it equals to m. So, well, this equals to m. So the only way that is possible is that you have something plus something that equals to twice the maximum. So the only possibility is that this equals the maximum and this equals the maximum, because it's not possible that something is higher than the maximum and this lower than the maximum, so the sum equals twice the maximum, because it's already the maximum. So we get that h of x0 over 2 is equals to m. So I do the same process by calling x n equals x0 over 2 to the power n. So I just I just divide this by 2 again, so it will be x0 over 4. X0 over 2 is inside 0, 1, and we do that process. I iterate this process, and by trivial recurrence, then h of xn equals m. So h of x0 divided by 2n equals m for values of n. So when I take the limit, it equals to h0 equals m. However, we already proved that h0 equals 0. So we know that for x inside 0, 1, h of x equals 0. So the function is identically equals 0. But since h is one periodic, then for values of x in the space of reals, h equals 0. Yeah, and h of x equals of f of x minus g of x, as we proved earlier. So f of x equals g of x, and so it's time to conclude the final results. So for x in the space of reals without the integers, we get that cotangent, that is the part of f. So cotangent pi times cotangent of pi of x, times x equals 1 over x, that is our g0, plus the sum of this, that is actually the g n's with n superior to 1, superior or equals to 1. So we get this result because it's just the sum. It's just the same way as we used. Where was it? It was a while ago. It was there. So we split this, that is equals to this, but not with x plus 1, just x. So we get, where is it? This. So we get this expression. So I can just split the sum because both converges. So I can write this by doing a change of value. So instead of, yeah, here there's a minus sign. So here I do a change of value, n equals minus n. So we get this. This transforms it from this to this. So I get that I get a sum between 1 and plus infinity, and a sum between minus infinity to minus 1. So I can just reunite the sum as a big one from minus infinity plus infinity, but the term on 0 is minus 1 over x. So oh yeah, and also this equals to this, because if you do the change of value, n equals minus n, since minus infinity will become plus infinity and plus infinity will become minus infinity, both are equals, so we get plus or minus here. So we get the famous Euler decomposition of cotangent, that is pi cotangent of pi of x equals to the sum from minus infinity to plus infinity of 1 over x minus n. That also equals to the sum from n equals minus infinity to plus infinity of 1 over x plus n. So that's the formula. But there are also, what the fuck is this word bug? I don't know. So we get also this formula that is just the notation using the ensemblist notation with z, because like you can do this. It's another writing of this, just just the notation of the sum. Also, you notice that if you do the change of value, x equals pi x equals pi x, well, x over pi. So you get the definition that is changed, because it's not z, it's pi over z. And also this becomes x over pi, and also this becomes x over pi as well. And then you can multiply by pi in the bottom and the top part of the fraction. And then you can factorize by pi, because you have pi here and pi here and pi here. So you get this expression. So you get that cotangent of x equals to the sum in z of 1 over x n times pi, and also instead of the minus you can get the plus 2 since it doesn't matter. And also there is the overriding between minus infinity plus infinity. And finally, you can multiply by tangent in both sides and get that tangent times this product, this sum, sorry, or tangent times this sum equals to 1. So yeah, that's the formula. If you have any questions, feel free to ask them in the comments. I'll be glad to answer them. And bye, thanks for watching.